They finished clearing out the tunnels and are now building the actual vacuum tubes that the the laser is going to pass through. There's also plans to put, there was actually a third LIGO built, but never installed anywhere. All the components are there, but they're not assembled. And that is intended to go into India. There have been some political difficulties in getting this to happen, but now that gravitational waves are sort of routinely being detected, India is much more excited about it. So that should happen sometime in the next 10 years, roughly. And then in the more distant future, there are going to be some space-based detectors. So if you've heard of, there was a recent buzz about this thing called ELISA, or LISA Pathfinder, which is essentially it's 3 satellites that are placed into orbit at very precise positions. They hold themselves in very precise positions, and they shoot lasers between them. And then they use the distance. Then when a gravitational wave passes through, they get moved. The lasers detect this, and this gives you a gravitational wave. So LISA is being engineered at the moment. I won't say built. And the intent of LISA is that it's going to be way bigger than LIGO. The laser, and therefore much more sensitive, and sensitive to a different frequency of gravitational waves. The frequency where supermassive black holes that are merging or orbiting each other would produce. So LISA will be sensitive to things like merging galaxies. And so that's, in the near future, that's something that's very exciting that should be coming, near-ish future, I should say. And the more distant future, there's more sensitive ground-based detectors and other things as well.
I think it's also worth pointing out there is a very different way that you can observe gravitational waves that people have been trying to do for about 10 years now, and unfortunately haven't had any success yet. But this is by looking at pulsars. These are spinning neutron stars that emit radio signals at very precise intervals. And if we precisely measure these arrival times of these pulses, and then look for sort of unexplained variations in them, then you could detect gravitational waves that cause the arrival times of these radio pulses to shift a little bit. But they still haven't detected anything yet.
But it's worth mentioning that they will. Pulsar timing arrays just get better with time.
Yes.
So essentially the way they work is they're trying to build statistics on sort of the amount of time it takes for these pulses to reach us. And so if you just wait long enough, you're going to get good enough statistics. And the other thing that I should mention about those is that they detect something very different from what LIGO or the gravitational wave detectors that have sort of been on the news so far detect. Pulsar timing arrays detect the background noise, the static from all possible gravitational wave sources in the universe. So in some sense, if you turn on your TV and you hear the static, if you're on the wrong channel, pulsar timing arrays are looking to detect that static, but for gravitational waves.
Neil.
What is the size and frequency of the gravitational wave?
Great question. So the frequency and wavelength is sort of the right question to ask. For the solar mass type objects that we've been hearing, or that we've detected so far, it's actually audible. And this is not quite the right frequency. It sounds, if you can play a sound on YouTube of exactly what this sounds like if you translate it to sound. It's on the order of like tens of hertz. And it sounds something like whoop. And if you sort of slow that down, that was the heavy black holes. If you take the neutron stars and you make it really much louder than it actually was, it's going to sound like a humming noise for a very long time, and then a whoop. And that's what you're hearing there, is that as the 2 stars get closer to each other, the frequency gets higher, because essentially the wavelength is essentially the diameter, the distance between the 2 stars is essentially what the wavelength is. And so the frequency is the wavelength gets shorter as the stars get closer, and the frequency gets higher. And they also get louder because they're more strongly emitting the closer to each other they are, because they're orbiting faster.
So that wavelength starts out in the range of tens of kilometers and then shrinks to...
Yeah, well, no, it starts at much more than tens of kilometers. Okay. It ends at tens of kilometers.
Yes. Okay.
It basically scales with the mass of the binary system for the merger frequency. So depending on the masses of the binary that merges, tells you in which frequency you can detect it actually. So the LIGO at this moment normally a stellar black hole regime, most sensitive to that frequency level. With LISA, as he mentioned, we will be able to look into the supermassive black holes, meaning that more than 1 million solar masses.
So it scales, like the frequency scales inversely with
Yes.
the masses.
Yeah, that's right.
Rick had his hand up a long time ago.
That's
Did you?
okay. I don't even remember what it was, but you answered it.
Okay. Yes.
About black holes, you said that this event led you to understand some things about the nature of black holes differently. Can you give us a few examples or things that you've learned?
Okay, first thing that's very important is for me personally is that for the first time we witness formation of a black hole. So this is not the first event that LIGO detected. Before they detected the merger event of two black holes, but they were already a black hole, right? So, but this time we actually witnessed a formation of a black hole in the universe. So that is very important. So when I say nature, what we know about black holes, we can basically define them with three parameters: the mass, the charge, and the spin. Theoretically, it's very hard to tell much about the spin of the black holes. But with the detections and more detections that we expect to have, we will be able to make a statistical data what are the general spins of black holes, which will tell us their formation scenarios. Theoretically, we say if binary black hole forms through dynamical effects in a cluster by colliding each other and so on, they must have a high spins. But interestingly, so far all the binary black hole detections LIGO has have an effective spin of around 0. So I said they don't have spins. That tells us something about how the universe, the nature, forms black holes. But of course 3 is not good enough to make statistics. So we need to have more. And then that will tell us about how they form, how they evolve.
And about the statistics, the LIGO has been running, well, I mean, the first detections were in September of 2014, but that run was only about 2 months long. And then it ran again in 2017 for about 8 months. And for therefore a total of 10 months, we have, I think, 6 binary black hole mergers and 1 neutron star merger out of just 10 months of observation. And then it was shut down again, and it's not going to be operational again until this coming fall. They do upgrades on these things, to make them ever better and so forth. And this next observing run should be longer, I believe.
Yep.
And hopefully, eventually we'll get to a point where gravitational wave detectors can be operating continuously, so we can see these things sort of routinely.
Well, then it will never be continuous, because often they shut it down because it's so sensitive that it's getting interference from like someone driving a car nearby or a thunderstorm or something like that. So that's never going to go away. But what is going to happen is there's going to be more of them. So at some point, enough of them will be online continuously. And also, the sensitivity is going to go up. So essentially, every time the detector gets more sensitive, it can see further away from us. And that means it can see a bigger volume of space. And so I think the statement, Jonas, do you remember how much more, what the increased rates should be?
Well,
The increased volume for, say, neutron stars? I think it's something
so
like
right
a
now
factor 8 for the next round.
sorry, the factor of?
I think it's like 8.
Yes, because the design, for design sensitivity, the range would be about 200 megaparsecs.
Yeah,
And so that's a factor of 2 in the range, which means a factor of 8 in
yeah,
volume.
so, exactly. So it's going to get twice as sensitive, but that's going to mean 8 times more black holes than neutron stars. So we're going to see a lot of these things.
Yes.
So I'm curious about the dynamic range of LIGO. That first detection a few years ago, there's 2 black holes merging, much more mass, much more energy released into gravity waves. This neutron star merger, I'm sure, was much less I think the black hole was, I don't know, 20 solar masses or something converted?
That's right, yeah. And this was one, so.
Okay, but were the neutron stars much closer to us than the LIGO?
Yes, by far, much, much closer.
Okay,
LIGO is, I think, more sensitive since that first detection, but the main reason we saw the neutron stars is just that they were really close this time.
Does this define some kind of limit to the size of black holes? What I've read, I think, sometime today about black holes was the minimum mass was estimated to be like 5 solar masses.
Right.
No, not that big.
There is no minimum.
Well, there is
For
an
stellar
observation.
There
evolution.
sort of is.
For
There's-
stellar
there is.
evolution black holes, yes.
Pardon me?
Yeah.
For black holes that are formed through the stellar evolution, yes. That's such a limit for the minimum mass you
For
can have.
like a merger or something like that?
Well, so essentially, suppose a star dies,
Uh-huh.
and the end of that death is going to be either a neutron star or a black hole. Neutron stars essentially can only be so massive because at some point the force, the pressure of the neutron stars, or the neutrons in the stars, is not strong enough to fight gravity. And so sort of the maximum mass of a neutron star, naively, would be the minimum mass of a black hole formed in that way.
Oh, okay.
But black holes could potentially form in other ways, and also
Okay.
it's possible that there's some range where, there could be some range where supernovae simply don't produce black holes for some reason. There's dynamics that we don't understand about the death of massive stars. But the naive picture would be that that's sort of the limit for black holes formed from the death of stars.
Very much smaller black holes could have been formed at the beginning of the universe.
Oh.
Primordial black holes.
Yeah,
that come from
maybe
the-
this was like like you were saying, the maximum size of a neutron. The maximum size of a neutron star would be 3 to 5 solar masses,
Yes.
somewhere in that.
So this
Because
is,
of the inability to resist.
and this is a major unsolved question, actually.
Oh, okay.
So the maximum mass of the neutron star has to do with how much pressure the neutrons can exert on each other.
Yeah.
And that has to do with the physics of how neutron stars interact, which is something we don't have a good handle on because our supercolliders on Earth cannot reach these incredible densities. And so neutron stars are sort of our only laboratory to understand this. And one of the major science goals of LIGO was to get a handle on the maximum mass of a neutron star because that tells us how neutrons behave at these high densities. So this is called the problem of the neutron star equation of state. And this one merger already gave us much more information than we had, but it's still unsolved. We need more.
But I think you said that it's most likely a black hole resulted from this merger.
Seems like.
What will definitively decide that question?
Well, we are looking forward to the electromagnetic observations, radiation observations of this. So if you look at the X-ray radiation from whatever is formed at the end of this merger event, already tells you something. The energy in the X-rays can tell you about the source of that radiation. So far, it's not. We are not 100% sure, but it's very much like it's a black hole now. Because the uncertainty in the initial masses of these binary neutron stars also makes us think whether it could be another neutron star what do you call them? Hypermassive neutron stars, things like that. But the follow-up observations, the electromagnetic radiation, tells us more about what kind of object formed at the end of this merger.
But actually, the question that you asked about the minimum mass of black hole is actually a really good question, and it is connected with a phenomenon that's called the mass gap. Because until this observation, it is true that the lightest black holes, we haven't seen any black holes or black hole candidates that were less massive than about 5 solar masses. So like the lightest black holes that we saw were 5 solar masses. The heaviest neutron stars that we saw were about 2 solar masses. And so there's this gap between 2 and 5 that we haven't seen anything in this gap. And so now with this neutron star merger, probably the remnant is a black hole with a mass of about 2.5, 2.4 solar masses. So that would make it the lightest black hole that we've ever observed. And a very good question is, like, so previously the lightest black holes that we observed, they're always in orbit with another star, and the star is losing matter that's secreted into the black hole, and that makes it shine, and that's how we observe it in X-rays. And so I guess it is possible that lower mass black holes only get created in neutron star mergers, and once the neutron star merger happens, there is no more matter around that could then light it up so that we could actually see those less massive black holes.
But I would like to make
sorry.
one thing. So this is, I'm a theoretician, so I need to be more specific on this. This is only if you consider that the black holes are formed through the end of a star. If you are thinking about the formation of black holes through primordial density distribution, so primordial black holes, they could have, in the beginning of the universe, they might have 10 to the minus 15 gram of mass. And they will last longer than the Hubble time of that. And they will be still around, but if they are not in a binary, we cannot see them, or we cannot notice their existence. So in principle, you cannot really put a limit if you think about all the black holes that nature can form. There's no mass gap. I mean, there's no reason for it. It's for the stellar evolution case that we have a gap to form for certain masses.
Yes.
I was curious, so the gravitational waves pass through everything and you can figure out the history of like the merger based on reading the waves of the detector, but how do you interpret what the waves have passed through or what was happening based on what the waves look like at the detector?
Okay, so I may have misconveyed a little bit of information there. What we learned from the gravitational waves is the motion of the mass that produced them. There's no real history after that.
Okay, so if it passes through something intermediate, like
Then-
since the merger, like you wouldn't know it.
Right, but that's an advantage because if light passes through something since the merger, it might get stuck in that something.
Right.
Stuff is dense, it reflects, it absorbs. So information about the thing that we're interested in might be lost because the light passes. Essentially, the light we see is carrying information about the stuff it passed through. Whereas gravitational waves, that's not the case.
But they interact with matter, right? So I mean, clearly they made the LIGO detector shrink and expand.
Yeah,
So,
it's a very
they
weak
lose-
effect.
Very weak effect, but they do lose some energy on the way, depending on what they
I
interact
suppose
with.
it's almost negligible. I mean, it really is negligible.
And so this fact actually also makes gravitational waves extremely interesting to study supernovae. So how a star collapses and explodes, because we see that happening all the time, but the light that we see from it comes from the very, very outer layers of the explosion, like millions of kilometers away from the central thing that actually provides all the energy for the explosion. But if there is a supernova in our galaxy, which happens roughly every, 50 to 100 years, and if we have, and we had a recent one close by that was in one-dimensional empty clouds in '87. But if one happens very close by, it also can emit some gravitational waves, and if we pick those up, then we would be able to say what is actually, we would get basically the gravitational waves would carry information from the very central part of the explosion of the supernova that carries information about how the star explodes and what actually powers the entire explosion. So that would be an extremely exciting discovery if it happens in our lifetime, but it may not.
Is it preposterous to imagine that LISA, for instance, might eventually detect information from before the universe was transparent? Because if its gravitational waves aren't blocked, are there events before that time that you could actually be detecting?
There is some hope of detecting that, but not with LISA.
Okay.
So those frequencies are actually going to be quite high. The only reason that they're low to us now is because the universe has expanded and stretched them out. So the expectation, I think, for primordial fluctuations is one needs a detector that is sensitive to shorter frequencies than LIGO is. But yes, people are thinking about that.
Is there a maximum size for a black hole?
Good question.
Repeat the
Good one.
question?
So
Maximum size.
What was the question?
Is there a maximum size for black holes?
Oh,
The size of the universe?
it depends on how fast they can grow, right? We have some black holes that we can observe, which we call them quasars. They are actively emitting black holes at the center of very, very massive galaxies. They have 1 to 10 billion solar masses at the center. And it's like only 700 million years after the universe, after the Big Bang, basically. But these are really the tips of the iceberg. Not every black hole can grow that rapidly and that much, because it depends on its